Do you think Dunkel is a good chem lab professor? Like, does he like instruct good?
Oh, it's a woman.
Sorry, she.
Yeah, she's teaching organic lab this semester, so she'll do a good job.
Okay.
You're talking about for next semester?
Yeah.
Yeah. Are you starting to sign up for classes for next semester?
Yeah.
Okay. Yeah, I don't teach any Gen Chem labs next semester because I have instrumental lab that I'm teaching. And Professor Scott is not going to teach next semester.
I saw that.
Yeah.
I've heard that Neimani, like they do different stuff than the rest of us do. Like they do the same stuff, but for like the graphs, they split it up into sections. So not everyone did every single graph.
Yeah, no, I can't, I'm not certain. But Professor Dunkel will be in charge of the labs next semester, so she's going to teach a couple and she'll be in charge. Okay, we'll go ahead and get started. Can the people on Zoom see my my screen and hear me?
Yeah, we can.
Thank you. So what we're going to do today is I want to just go over the quiz 3 answers, and then we'll finish up the lecture portion of chapter 6. And then I want to go and pick out a few of the homework problems and just kind of review those. Then that'll finish off chapter 6. And on Wednesday of this week, we'll have a review session on chapters 5 and 6. And then next Monday, we'll have the exam on chapters 5 and 6. So any questions about any of that? Okay. So for quiz 3, which is on chapter 5, the first question, electrostatic attraction is seen between oppositely charged ions. That's true. That's the old opposites attract thing that we've talked about. Number 2, the first law of thermodynamics says that energy is either created or destroyed when it is converted from one form to another. That's false. Energy is neither created or destroyed. That's the key thing to the first law of thermodynamics. Number 3, when heat is absorbed by the system from the surroundings, the process is endo or exothermic, and the answer is endothermic. So if it's absorbing the heat, it's endothermic. Then we had a few calculation type problems. So let me scroll down to that one. So in number 4, you needed to calculate delta E, and you were given the formula that delta E equals heat plus work. So calculate delta E if a system releases 66.1 kilojoules of heat to its surroundings, while the surroundings do 44 kilojoules of work on the system. So the key thing to this problem was if it releases heat, if the system releases heat to its surroundings, and that's exothermic, so the sign on that would be negative. And then if work is being done on the system, then that would be endothermic, so the sign on that would be positive. So you needed to get the signs correct. So then it would be delta E equals minus 66.1 plus positive 44.0 kilojoules. And then the answer was minus 22.1. So once again, the key there was understanding if the kilojoule value for heat or work needed to be plus or minus based on, was it endothermic or exothermic? Okay, for number 5, you're giving a reaction, and then you're giving a delta H value, and you were given some atomic weight information. And the question was, how many grams of magnesium oxide are produced during an enthalpy change of minus 234 kilojoules? So if you started with minus 234 kilojoules, you wanted to get that converted to grams. And we know that when we're trying to get something into grams, moles is probably going to be involved. So we knew for the reaction that delta H was minus 1204 kilojoules. And from the stoichiometry of the reaction, we knew that 2 moles of magnesium oxide are involved in that reaction. That's what's formed. So we know that for every 2 moles of magnesium oxide, that we have this minus 1204 kilojoules. And so we use that relationship. So by putting the kilojoules in the denominator, kilojoule units cancel, and now we're into moles of magnesium oxide. We wanted to get to grams of magnesium oxide, and we know that the relationship between moles and grams, we get that through the molecular weight. So then if you used the atomic weight information, you could calculate the molecular weight of magnesium oxide, and that comes out to be 40.3. That goes in the numerator because we want to now cancel moles of MgO. And so the mole of MgO is in the denominator, our units cancel there for moles, and we wind up in grams of magnesium oxide. And that value is 15.7 grams. So in this problem, the key was using the stoichiometry of the reaction to see that for this delta H, that's for the production of 2 moles of magnesium oxide. And then knowing that we need to use molecular weight to convert from moles into grams. Okay, and number 6, if the specific heat of water is 4.18 joules per gram Kelvin, what is the heat capacity of 185 grams of liquid water? So if we look at the units, we have grams that were given of water, and then we have this specific heat value, and the units of that are joules per gram Kelvin. And we see that in the joules per gram Kelvin, the grams is in the denominator, So if we multiply grams times that, the gram units will cancel, and then we'll be left with joules per Kelvin. And that's what we want. So 185 grams times 4.18 joules per gram Kelvin results in 773 joules per Kelvin. So once again, just as in the previous problem, by lining up our units correctly and making sure that the units are canceling out the way we want them to, we can set up the problem, and then it's a matter of doing the calculation. Number 7. So number 7, I messed up on. So the question was the specific heat, and then, excuse me, and then the formula for specific heat is given there. Of octane is 2.22 joules per gram Kelvin. How many joules of heat are needed to raise the temperature of 90 grams of octane from 15 to 25 degrees C? Well, a couple of you pointed out to me that there was something wrong with this question, so thanks for doing that, those of you who did. Surprisingly enough, about half the class got the right answer, even though I put the wrong weight of octane in. So originally, in your question, it was 90 grams. When I did the math on 90 grams, I didn't like the answer that it came out to be, so I switched it to 95 grams. Unfortunately, I didn't switch it in the question, just in the answer I generated, so that's my fault. So if you happen to get the right answer, you got the points. If you got the wrong answer, I went back and gave you the points. So no one lost any points on this, and I do apologize for that mistake. So it should have been 95 grams of octane. If you put 95 in there, then you get 2.11 times 10 to the third. But let's talk a little bit about how you do the problem. So we're trying to find that heat value. We're given specific heat, which once again, the units on that are joules per gram Kelvin. And we know that M in our formula is mass. And so that would have been the 95 grams if I put that in correctly. And then delta T is that temperature change. And so there's a 10-degree temperature change. And remember, when we talk about temperature changes, and whether it's C or K as the units, in each case, it would be 10 either way. So in this one, you didn't actually have to change it to degrees to Kelvin. You could leave it in degrees C, because it's that difference that you would want. Okay, so now the last one. Number 8. You were given 2 reactions, 2 half reactions, and then given the delta H for each of those. And then you needed to calculate the enthalpy of the reaction of nitrogen to produce nitric oxide. And so what you needed to do is you needed to rearrange those 2 equations at the top, those 2 half reactions at the top, to be able to get the reaction of what we wanted. So the N2 plus O2 going to NO. And if you look at the first equation, N2 plus O2 going to 2NO2, we see that N2 and O2 are on the left-hand side of the reaction, which is what we want. And the second equation, we see that NO and O2 going to NO2, we see the NO is on the left-hand side, but in our reaction that we're studying, NO is on the right-hand side. So you needed to flip that second reaction around. And remember, the delta H value for NO plus O2 going to NO2, that's minus 114.2. If we turn the reaction around, the magnitude of the reaction stays the same. So in other words, the number stays the same, but the sign has to be changed. So when we added up these delta H's to see what the final answer is, we would have plus 66.4 kilojoules for that first reaction. And then the second one, because it's flipped, it's now plus a positive 114.2 kilojoules. And you add that up and you get plus 180.6 kilojoules. So any questions on the quiz problems? Okay, give me a moment here to pull up chapter 6 slides. Okay, so when we left off, we were starting to talk about electron configurations. And so the electron configuration is kind of the shorthand way we write to show energy levels of the electrons and what orbitals they're in and things like that. One of the real important things about electron configurations is that what you'll learn is that the valence electrons, so those outer shell electrons, are really where all the reaction chemistry for the most part happens. And so those valence shell electrons are really important to understand how things bond and react and absorb energy, emit energy, things like that. So having a shorthand way of expressing those valence electrons is real important for understanding that. A lot of periodic tables will have actually the valence shell electrons spelled out on them. Not all of them, but a lot of them do. And that's because those are the electrons that really all the action happens at. The inner shell electrons, those are much more stable. It takes a lot more energy to do something with those. So while it's not impossible, that's not really where most of the activity occurs with compounds. So we talked last time a little bit about orbital diagrams, and we had this example of where we have the atom listed, then we have these little boxes, and we'll have arrows going up and down, and those arrows, those half arrows going up and down, represent electrons. And we talked about how going up and down signifies two different spins, plus a half or minus a half. And so we also talked about how when we put them in, if there's only one there, by convention, we always draw the arrow facing up. And so that's why in this example for lithium, the 2s arrow is facing up. We also talked about how each of those boxes is an orbital, and we started to talk a little bit about how we fill those boxes. And so that's what we're going to continue on with today. There's something called Hund's rule. And so when filling degenerate orbitals, the lowest energy is attained when the number of electrons having the same spin is maximized. So what that means is, first of all, does anyone remember what degenerate orbitals meant? Degenerate orbitals just means that all of those orbitals have the same energy. And so, and then in this rule, we're talking about degenerate orbitals with the lowest energy is attained when the number of electrons have the same spin. Why do we want the lowest energy? We want the lowest energy because that's going to be the most stable configuration. And so by most stable configuration, I mean the one that you're most likely to find. And so what Hund's rules also means is that when you're at a particular sublevel, there needs to be one electron in each of them before you start pairing them. And we have some examples here, so let's just go through these again. The lithium we talked about, beryllium, that one's kind of obvious because you fill the 1s with 2 electrons, and then building off of the lithium, you would add that second electron to the 2s orbital before you went to 2p. Let's skip down to carbon, or rather, let's skip down to nitrogen. So nitrogen, what we see is we have the 1s and 2s that are filled. Then we put 1 electron in each of the 2p orbitals. And so you see a couple of things here. One is we don't start pairing anything in the 2p yet. And that's where Hund's rule comes into play. We're going to have all of these 2p orbitals, each with 1 electron in them before we start filling. So so they skip to neon at 10, but if we went to 8, then what we would see is that first box under 2p would now have 1 arrow up and 1 arrow down. And then it would be 9 would be 1 arrow up, 1 arrow down in the first box, 1 arrow up, 1 arrow down in the second box, and then 1 arrow up in the third box. When we get to neon, if you recall, is in that 8A group. And so that's the noble metals, or noble gases rather. And those noble gases have a full shell, we call it. So you see you have 1s is full, 2s is full, 2p is full. And so we'll see in a little bit here that there's a shorthand way to express things based on how those noble gases fill. And so there you would have the 1s shell fully filled, and then the 2 shell fully filled with 2s and 2p filled. So then when you go to sodium, then you move up to the 3s energy level. So this is what I was talking about, using the noble gas a little bit, and we'll talk about this a little bit more. So elements in the same group of the periodic table have the same number of electrons in its outermost shell. And that's those valence electrons I was talking about. So in this example, you see they have the 1A elements. They have lithium, sodium, potassium, rubidium, cesium, francium, on down the line there. And what you should notice is the way they have it written is the thing in parentheses, like for lithium, for instance, they have helium in parentheses. For sodium, they have neon in parentheses. What that is implying is that you have the electron configuration for, in the lithium example, for helium, and that's what's implied by that helium in parentheses. And then outside of that, for its valence electrons, in this case, it's 2s1. For sodium, its electron configuration would be the configuration for neon. And then 3s1 would be its valence electron. That inner shell of electrons, so in other words, represented by the helium or the neon or argon on down the line there, the thing in parentheses, those are called the core electrons or the inner electrons. And those are the ones I was saying before, that it's a little harder to do things with those electrons. And so that's one reason why there's two reasons people will write stuff with the shorthand. One is you don't have to write as much stuff out, so a practical type reason. But the other reason is all of these elements in this example, these 1A elements, are going to behave similarly because they all have one valence electron. And as I said before, it's that valence electron that is the most active electrons. You need valence electrons. And so this kind of cuts to the chase of the ones that were most likely to have some activity with those valence electrons. So this is kind of that example there of those electron configurations. That's kind of a shorthand version of writing the full electron configuration out. Okay, let's talk a little bit about the transition metals. So if you recall the transition metals, and hopefully you remember this from the lab this past week, the transition metals, on the far left, those first two columns, and then it kind of dips down and then dips back up when you go to the right a little bit. It's those ones in that dip area. I think we have a photo of it in a little bit, but those are the transition metals. And so what the example we have here is, we're talking here they're talking about, first they talk about argon. Argon, atomic number 18. So it's one of those noble gases. It ends period 3, and here's its electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6. Potassium, which is the next one in the periodic table, you might think, well, okay, I know from my quantum numbers that the 3 is going to have d orbitals. So maybe the next thing would be 3d with one electron in that. But on the energy level diagram we see on the right, we see that from an energy level perspective, it goes 1s, 2s, 2p, 3s, 3p, but instead of 3d, it's actually 4s is the next energy level. So that 4s, even though it has that quantum number 4, it's less energy than 3d. So 4s is what we'll fill next. So that 19th electron, so that next electron, will go into the 4s orbital rather than the 3d. After you fill the 4s, so that's, once again, that's those first two columns, 1A and 2A, those first two columns will fill the 4s. Then when we get to the transition metals, which are next, then we start filling the 3D orbitals. And so for me, an easy way to remember that I want to fill 4s before 3D is just the fact when I look at the periodic table, I see those transition metals kind of sunk down a little bit. And there's 2 electrons to get there. Well, if I were to put 2 electrons into the 3D orbital, so I could put 2 of them into the 5 3D orbitals, but I would just have 2 electrons in 5. If you put 2 electrons in the 4s, that fits nicely and it fills it up. So just from a stabilization point of view is how I look at it, that makes a little more sense. And by, like I said, looking at that periodic table and seeing those 2 columns for the 1A and 2A elements, then kind of seeing that drop down on the transition metals, that's my way of remembering, okay, for those transition metals, That's when we start filling the d orbitals. Lanthanide and actinides are where we start filling the f orbitals. It's a similar kind of logic as we talked about for the d orbitals. And you can see here the lanthanides are atomic numbers 57 to 70. And that's when you start getting electrons in the 4f sublevel. The actinides, that starts around higher and you get to the 5f. To be honest, we're not going to spend much time on lanthanide or actinide. I would much prefer that you focus on the transition metals and get comfortable with how those orbitals fill, rather than spending a lot of time on lanthanides and actinides. Not that these aren't important, but I think at this stage, it's better to get the transition ones under control and not worry as much about these. So this is what I was talking about a little bit with the periodic table and how it's helpful in understanding how these things fill. So here they're telling us the different blocks of the periodic table correspond to different orbitals. So the two on the left, the 1A, 2A, that's kind of a bluish color, those are s orbitals. Over on the right, combination of metals and nonmetals and metalloids, the pink one, those are p orbitals for the most part. Well, they're the p orbitals. D, the transition elements, which we talked about, are the transition elements. And those transition metals are the orange on this. And the way they have this drawn right now, it's a little deceiving. The lanthanides and actinides, those intertransition elements, usually if you think of the periodic table, those are kind of stuck down with a little arrow down to them on the bottom. And then the 1A, 2A go over there next to the transition metals. So it looks a little bit different in this representation. But I would suggest focusing on the S, the P, and the D. Those are the ones that are most common and the ones you typically deal with. The S and P ones, so the 1A and 2A, and then the pink ones over on the right. So that'd be 3A, 4A, 5A, 6A, 7A, 8A. Those elements are called the main group elements. This is what, if you think about how we normally see the periodic table, this is what I was saying about those lanthanides and actinides. This is with that little arrow showing that kind of light tan color at the bottom. This is more what you're used to seeing, and I think this is more useful. If you're going to memorize something, memorize this. And what it's telling you is over on the left there in the blue boxes, those are those s orbitals we talked about. 1s, 2s, 3s, 4s, 5s, 6s, on down the line. Over on the right-hand side in the pink reddish ones, that's where you have the p orbitals. And so those are going to fill. And so if you think about it, we know that s, there's one s orbital. And so that's 2 electrons. So that these ones on the left fill that. We know for p, there's 3 orbitals. And each of those hold 2. So that's 6 electrons. So you see those are 6 spots there, 6 electrons there in the pink area. And then D, there's 5 orbitals. And so you have 10 electrons there. And that works out there that if you fill those transition elements, that's 10 electrons there. So it really works out pretty well. And this kind of way of writing electron configuration works for most elements. You see on the slide, most is in bold, and that's because there are a few exceptions. And we'll talk about those a little bit and why those are there and kind of the reasoning behind it. The one thing that I'll just say before we get to those exceptions is that when we think of electron configurations, one of the things that we're always trying to do is get to the most stable configuration. Lowest energy, we said, is more stable. And also, you know, we talked about things about not pairing the spin until we fill an orbital, a set of orbitals and things like that. So we're always trying to come up with the configuration that from a stability perspective is most stable. So in this example, they're talking about selenium, and we see that they've written it with the shorthand method of having the noble gas argon in parentheses there, indicating that all of those electrons shells are filled. And then we go to the fourth row and we fill 2 electrons to fill the 4s. So that's the 4s2 shorthand. Then we fill the d electrons, the 3d electrons, and that's full. So there's 10 of those. And then finally, then we get to the p electrons over in the pink area there. And so then we would have 4 electrons in the p orbitals. So that selenium with the argon in parentheses and 4s2, 3d10, 4p4, that's what we're talking about when we're talking about electron configurations. And in this case, we're representing those core electrons with the argon in parentheses. So you do see some differences when there are enough electrons to half fill s and d orbitals on a given row. And this gets back to that what I was talking about, is sometimes you'll have a little bit different filling when it allows you to have 2 half-filled orbitals. So in other words, have half-fill s and half-fill d. That gives you a little more stability. So we'll take a look at that in a moment here. And here's an example of one of the periodic tables where they have all of the valence electrons configurations listed on the table. So if we look at chromium, for instance, so chromium fills as argon shell, inner shell, and then 4s1, 3d5. And normally, you would think it would be 4s2, 3d4. But if we go back and look at where chromium is, let's see. So chromium there you see is number 24. So that's the third row, column 6, third row. And so we're filling those s orbitals, and then we're filling d orbitals. And we get to chromium and we have 1, 2, 3, 4 electrons that would go into that d orbital. By taking one of the s electrons and putting into d, into the 3d orbital, now we have a half-filled 4s shell and a half-filled 3d shell. And similar thing happens with copper, where we get some half filling of shells there. So in that case, we do 4s1 and 3d10 rather than 4s2, 3d9. This happens because the 4s and 3d orbitals, while there are differences in energy, it's not a big difference. And so you actually get more stability even though you go up to put an extra electron in a higher energy level. In other words, put an extra electron in 3D level rather than 4s, that by doing that, it's actually overall a lower energy than if you kept the 2 electrons in 4s. So in the chromium example, you're half filling that 3D shell, in the copper example, you're going ahead and fully filling the 3D shell and half filling the 4s shell. So just as kind of a rule of thumb, a half fill shell is a good in terms of stability, whereas partial ones aren't as stable as half filled ones. So sometimes you have examples like this, where by shifting one electron where the energy levels are pretty close, you can get either a full filled shell or half filled shell that gives you a little more stability. You see this also when you're talking about those F block atoms. And so remember, that's the lanthanides and actinides. And so there's some of this kind of like shifting with F and D orbitals as well as these S and D ones that we did here. Like I said, for my opinion, we're going to focus on these S and D ones and not worry as much about the F ones. So there is some homework associated with this. You know, the expectation for the exam is that you would be able to write electron configurations, both using that shorthand with the noble gases, but also doing it from start. So in other words, not just, you should be able to do it whether you're starting from the 1s, 2s, 2p on down the line, the whole thing, or you should be able to do it using the shorthand, using the noble gases. The other comment I'll make about that is, I haven't made the exam up yet, but there will be electron configuration questions, and I'm not certain if that can be a multiple choice question or not. So if it's not, then it would be a case of where you'd have to just write it out and then, you know, make it a PDF and submit it, kind of like you do on your labs. So if I can figure out how to ways to do that multiple choice, I will do that, but I'm not certain if that's possible. So that wraps up the lecture part of chapter 6. Oh, or does it? Hold on. Yeah, it does. And so any questions on any of this? Because what I'd like to do next is kind of go through some of the homework problems for chapter 6. The ones that we talked about last lecture, and then the ones that you see on the screen now. Okay, if there are no questions, then I'm going to go ahead and pull up some of this and kind of just review some of this. Okay. Okay, so the first one is 6.55. I'd like to go over. So here they give us the principal quantum number 4, and then they ask, what are the possible values of L? And remember, for L, to find those values, it's n-1 to 0. So in this case, it would be 3, 2, 1, and 0. So if you're given, like we're talking about here, if you're given a particular quantum number, you should be able to figure out what an associated quantum number is based on the quantum number that you're given. And so what I will say is on a quiz or exam, you're not going to be told that L equals n-1 to 0. That would be something you would be expected to know. And then like on the next one where they're telling us L equals 2, and they want M sub L, you would be expected to know that M sub L is equal to -L to plus L, including 0. So in this example, if L is 2, then M sub L would be -2, -1, 0, +1, +2. And then the third one, once again, if M sub L equals 2, what is L? And that's -L to +L. So 2, 3, and 4. Okay, let's look at (6.57). So what are the numerical values for N and L corresponding to each of the orbital designations? So for 3p, we know that the principal quantum number is 3 because of the number 3 there. And then remember we said with the L's, while they have a number, we don't use the number when we talk about them. We use, this is where we have S, P, D, F. And so for L equals 1, so for L equals 0, that's S, we see that. But L equals 1, that's P. So we know that 3P means the N quantum number was 3 and the L quantum number was 1. On B with 2S, once again, we get that principal quantum number from the number in front of it, in this case 2. And then since it's an S orbital, we know that means L equals 0. For 4F, principal quantum number N equals 4, and F designation tells us L equals 3. And then the last one, 5D, N equals 5, so N, that principal quantum number N is 5, and then since it's D, L equals 2. So S is 0, P is 1, D is 2, and F is 3 for those L quantum numbers. Once again, that's something that you would just need to memorize and be expected to know. Okay. So let's look at 6.71. So for 6.71, the question is, what is the maximum number of electrons that can occupy each of the following subshells? And then we're asked about 3p, 5d, 2s, and 4f. So an easy way to remember this is think back to that periodic table. And so, actually, let's see if I can go back there just to show this. So this is where, if I think back to the periodic table, and I have a periodic table handy, I talked about how the S shell are these 2 columns on the left. So that tells me that's 2 electrons. I said the P are the ones over to the right, in this case that's shaded in red or pink. And so we see how many electrons are in the P shell, and that's 6. There's 6 electron spots there. And then D is that transition node. So in this case, it's colored orange. And if you count how many slots there are across those transition metals, then that is 10, and that's the D. And then F was that actinide, lanthanide, and I can count those up, and that would be 14. So if you can just kind of visually remember kind of this color scheme on this, and you have a periodic table handy, I think it's easier to remember how many electrons go in each of these shells. The kind of 2 things on the left that hang out, those 2 columns, there's 2 slots there. That's the S. Over to the right, the stuff that's kind of hanging out to the right, that's the P. And so you know how many are there from that. And then the 10 in the transition metal area. And then finally the 14 in the F level, that's kind of the thing that's arrowed out. So I think this is a table here that personally I find this kind of presentation real useful in helping me remember how this stuff goes. So let's go back to the question. 671, so thinking back what that looked like in our mind, we know that P is 6, D is 10, S is 2, F is 14. The answer doesn't change even if it was 4P or 3S or something like that. And that's because we're talking about the valence electrons. And remember, we mentioned that with the valence electrons, it's in the columns, they'll have the same number of valence electrons. It's just the number of core electrons or inner shell electrons that varies. But the valence ones in those columns stays the same. So in this case, like I said, they're saying 3P, but if it was 4P, it would still be 6. Okay, let's look at 73. So some questions. What is a valence electron? That's those outer shell electrons. And we said those are the ones that are going to be involved in chemical bonding. Those are also the ones that are really involved in the energy transitions as well. And so those outer shell electrons, those valence electrons, is where a lot of the activity, a lot of the action occurs. And then what are core electrons? Those core electrons are the ones that make up that base noble gas configuration. And so that's why sometimes we write our electron configuration in a shorthanded way so that those core electrons are represented by the noble gas symbol in that kind of boxy parentheses looking thing. Then the next question, what does each box in an orbital diagram represent? So each of those boxes represents one of the orbitals. And since it represents one of the orbitals, that's why we have the 2 electrons, the 2 arrows, up or down. And then the last question, part of this question, what object is represented by the half arrows in an orbital diagram? What does the direction of the arrow signify? So those half arrows represent an electron, and the direction represents the spin. And when we draw them in those boxes, we first draw them all facing up. And then once we do that, and remember that was the Hund's rule thing, then we go back and we start pairing, and then they'll go down in the down direction from there. So these are some definitions that you should know. Kind of understanding the difference between valence and core electrons and why that's important. Okay, 675. Write condensed electron configurations for the following atoms using the appropriate noble gas core abbreviation. So we look at this, and so we would go back once again, just to reinforce this. We'd go back to kind of this representation to kind of see how things fill. See the S, then the D, then the P, and kind of see when that happens. So first we fill 1S, then 2S, 2P, 3S, 3P, 4S, 3D, and on down the line. So usually if you practice a little bit, you get the hang of it. And so in this case, If we would go and look up cesium, we would see that xenon is that core. And so cesium is just one of those 1A elements. And so we go back here. Once again, let me show you this one. You see cesium is number 55 down there, second from the bottom above francium on the far left. So we see that we fill xenon, that's 54, and then we have one more electron to go. So now that's the 6s shell. And so it'd be 6s1. And sure enough, it's xenon is the core, and then 6s1. Nickel, if we look that up, we see argon, and then we fill 4s2, 3d8. We don't get any, we can't go and fill the 3d and get 3d10 because then we have nothing in the 4s. So we had some other examples of where we had one electron in the s to fill a d level, but we still had that one electron, so we could have half fill. You're not going to have 0 in a shell and then jump to a higher energy level. You might have it half full, but you're not going to have 0. So in this case, we can't take one of those two s electrons and shift them to the d level. So 4s2, 3d8. Selenium, once again, we have argon, then we have 4s2, 3d10, 4p4, cadmium, 5s2, 4d10. Here we have an oddball one, and this gets into some of those F levels. So we have 5f3, 6d1, 7s2. That's an unusual one in terms of how it's filling. And so for that, to know that one, you would have had to have just kind of memorized it or looked it up or something. And then finally, lead, 6s2, 5d10, 6p2. So the takeaway on this, and we'll do this again just because I want you to realize the importance, is we go back to here and you should know how they fill. As I said, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, on down the line. You should understand how they fill and then be able to kind of fill things in based on that kind of logic, okay? And you should be able to write it in this shorthand method with the noble gas as the core, or you should be able to write it as, for instance, in this one, you go ahead and write out 1s2, 2s2, 2p2, 2p6, 3s2, on down the line. Is go ahead and write them all out. So in other words, write out the argon part as well. So either way, you should be able to do it. There is another way that people will write this sometimes, is that they'll literally show the electrons, so the up and down arrows. But this is the more common way that shorthand that you'll see written. Okay. Let's look at 6.79 for a moment. So it says the following do not represent valid ground state electron configurations for an atom because either they violate the Pauli exclusion principle or because orbitals are not filled in order of increasing energy. Say why these aren't good. So the first one, 1s2, 2s2, 3s1. The problem there is that if we go back to our periodic table, we see that we should be filling the 2p orbitals before we start filling the 3s. And so that's the thing that's violated there. In B, we have 6s2, 5d4. Once again, in this case, before we started filling those 5d orbitals, we should have filled the 4f orbitals. And then finally, the last one, 3s2, 3d5, you'll fill 3p before you fill 3d. And how do we know these things? We go back to this presentation here, and we see the order in which the S's are filled, and the D's, and then the P's, and then when the F ones start coming in there. And we also see kind of what that principal quantum number is. So we see 4s2, then 3d10, then 4p, and it would be 5s, 4d, on down the line, 5p. And so, like I said, if you're gonna memorize one slide, this is the one I would memorize, because I think having this information here combined with the periodic table helps you understand how these valence electrons fill up. Any questions about this homework? Okay, let me scroll over to the previous stuff. Okay. Let's take a look at 6.19. So in 6.19, they're asking, what is the frequency of radiation that has a wavelength of 10 microns? And so hopefully you remember the formula, that frequency equals the speed of light, which is a constant. That's 2.998 times 10 to the 8th meters per second, divided by the wavelength. So in this case, we're trying to find the frequency. But let's look at our units for the speed of light. They're meters per second. We were given a value in microns. So here you need to remember the conversion from microns to meters. And a micron is 10 to the minus 6 meters. So by simply taking that 10 micron value, which I have in the denominator here, and multiplying it by 10 to the minus 6, I've converted it into meters. So 10 times 10 to the minus 6 meters is the same as 10 microns. So it's not difficult in terms of math, but you have to make sure that if you're using this formula, and this is because of the units on the speed of light being meters per second, you have to make sure that your wavelength is in the right units. So if you leave it in microns or you don't convert it appropriately into meters, then you won't get the right answer. So if you do that, you can do the math and you get your frequency. And remember, the units of frequency is seconds to the minus 1, also can be written as 1 over seconds, and it also can be written as hertz, Hz. So any of those three designations mean the same thing and are commonly used for frequency. So in part B, they're asking for the wavelength that has a frequency of 5.50 times 10 to the force seconds to the minus 1. So once again, we use that same formula, which tells us that frequency equals the speed of light divided by wavelength, except now we're going to be solving for wavelength. And so if we solve that, we get 5.45 times 10 to the minus 7th meters. Wavelength is typically expressed in nanometers. And so if you recall, nanometer is 10 to the minus 9th meters. And so that's where you would convert this 5.45 times 10 to the minus 7 meters to 545 nanometers using that 10 to the minus 9th conversion factor. Okay, then in C, they're asking, would A or B be in the visible region or not? Well, once again, what you would want to do, because when we talk about light, we talk about radiation like that, we're usually talking about it in terms of nanometers. So you'd want to convert those answers. In the first one, in part A, 10 to the minus 6 meters, you would want to convert that to nanometers, and that's that conversion of 10 to the minus 9th meters is 1 nanometer. And then you get 10,000 nanometers. Well, that's not the visible range. We know that from that chart we had. I don't remember what 10,000 nanometers is, but it's pretty far away from visible. Then the second one, if you convert that into nanometers, which we had already done, that's 545 nanometers. That's visible, because the visible goes from 400 to 750 nanometers approximately. And then finally, part D asked, what distance does electromagnetic radiation cover in 50 microseconds? So if we think of light, we have a constant which tells us the speed of light. And that's that 2.998 times 10 to the 8th meters per second. And we're given a value that's a time value, microseconds. And so we know that if we have a distance per time constant, if we can get rid of the time of that component of that, then we'll just have distance. If it's in seconds and we're in microseconds, we need to know, we need to change that microseconds into seconds. So once again, this is remembering what those prefixes mean. Just like we said, microns, micrometers was 10 to the minus 6. Once again, we get that here. It's going to, that micro designation means the same thing, whether it's seconds or meters or whatever. And so we can convert 50 microseconds into seconds by using that 1 microsecond is 10 to the minus 6 seconds conversion. And then we can then cancel out our seconds by multiplying that by the speed of light, and we get the distance, in this case, meters answer. So one thing I hope that you're starting to see, whether it be these problems or other problems, is that at the very beginning of the semester, we talked about dimensional analysis and setting up problems, using the information that you have available to set up problems in a way that you get your units into what you want them to be ultimately in your answer. And if you can get in that habit of writing the stuff out and having it set up so you can clearly see if you're canceling the units out correctly, I just think that's a real key to solving these or any of the problems we talk about. At least it gives you a pretty good chance of getting it answered correctly. Okay, let's go to the next one. So 625. So in 625, we're talking about calculating the energy of a photon whose frequency is 2.94 times 10 to the 14 seconds to the -1. So once again, we use our formula here. Energy equals Planck's constant times the frequency. So we've talked in lecture about how energy is proportional to frequency, and we see that here. And so then it's a matter of making sure things are in the right units. We're given a seconds to the -1 frequency. That unit's going to cancel well with the joules second and leave us just with joules. So then it's a matter of just making sure that we're comfortable using our calculator to do some math where they each have exponents and scientific notation and all that kind of stuff. So if you're confident of that and you've checked your units, you should be good and you get the valid answer that we have here. In B, part B, we're saying calculate the energy of a photon whose wavelength is 413 nanometers. So in order to use our equation, we need to get things changed into frequency. And once again, we can use the speed of light. That's the 2.998 times 10 to the 8 meters per second rather. And wavelength was given in nanometers. As I've said before, that's a pretty common way to see wavelength expressed in as nanometers. So I want to get it into meters so that it'll cancel the units on my speed of light constant, get rid of those meters and just have it in seconds to the -1, because I know that that's the unit for frequency. And so I convert that 413 nanometers into meters by making it 413 times 10 to the -9. And then if I do my math, then I get a frequency value. So now that I have a frequency value, I can go back and use my energy calculation formula. The energy equals Planck's constant times frequency. I put the Planck's constant number in. I have my just calculated frequency that I got using that speed of light relationship and wavelength frequency relationship. And then I get an energy value in joules. Okay, then in C, what wavelength of radiation has a photons of energy 6.06 times 10 to the -19? So this is kind of like the backwards of B. So I have energy. I can use that energy equals Planck's constant times frequency formula to find the frequency. And I go ahead and do that. Then I go and use my formula, which relates frequency to wavelength, using that relationship in conjunction with the speed of light, plug those things in, and then I can solve for what the wavelength is. Since I normally like to talk about wavelengths in nanometers, expressed at both as meters and nanometers. So a couple of relationships here that you should know. One is the Planck's constant one between energy and frequency. The other is the one that relates frequency and wavelength, that those are inversely proportional. And that involves that speed of light constant. So if you can remember those relationships, you should be in good shape with that. Okay, let's look at 631 for a moment. So in 631, it tells us that a diode laser emits wavelength at 987 nanometers. It's what region is this? So if you So we could look that up and know that it's the infrared region. But in part B, energy absorbed. So you have 0.52 joules over a period of 32 seconds. So in this one, once again, we can use that relationship between energy and frequency. So we would have to calculate our frequency, and we do that, it's listed up there in part A. That's that formula we were talking about before, where we use the speed of light and then that inverse relationship between frequency and wavelength. So frequency is the speed of light divided by wavelength. We plug those in and we get a frequency for this laser. We can then use that frequency value to calculate energy, because we know from our formula, energy is directly related to frequency involving Planck's constant. And then we get a value of joules per photon. Well, now what we need to do is we need to get our units changed a little bit, because we have an energy value where we say 0.52 joules over 32 seconds. And we know that one photon gives us 2.01 times 10 to the minus 19 joules. So by flipping that arrangement, we now get our joules to cancel. So we see, once again, that by looking at dimensional analysis and getting our units, because we said we wanted to wind up in photons per second, if we get our units to where we want to be, we know we have to invert that joules per photon value to get joules to cancel out, and now we're going to have units of photons per second. And then we can just go ahead and do the math on that. So the idea on these kind of problems is there are a few relationships you need to be comfortable with. Ones that relate energy to frequency, one that relate frequency to wavelength, things like that. Understanding which constants go with which formula. Understanding, depending upon what you're trying to calculate, which of those formulas you need to use. And then lining up your units in a way so that things cancel out appropriately. If you do all that, you should be in good shape. So I'm going to stop for now. On Wednesday, we're going to go back through chapter 5 a little bit and review that. We'll review this chapter again. Please go ahead and try some of those electron configuration problems and things like that that were assigned at the end of the chapter. And we'll kind of review 5 and 6 on Wednesday, and then next week on Monday, you'll have the exam on chapters 5 and 6. Any questions about anything before we go? Okay, thank you.